and you get nothing at all, then you're pointing at the wrong spot. Yes. Let me do this green box. Yeah. Turn this up here.
Can you explain again what the curly brackets were for?
Yeah, so the curly brackets refer to the fact that I put an exclamation mark at the front, which means the rest of this is not a Python command, it's a bash command. And bash doesn't know about capital path because capital path is part of Python. So this is a special Jupyter thing which says expand this Python thing, please, before you pass it to the shell. Good question, thank you. So the goal here is to use the training set, which contains data through the end of 2011, to predict the sale price of bulldozers. And so the main thing to start with then is, of course, to look at the data. Now, the data is in CSV format, right? So one easy way to look at the data would be to use shell command head to look at the first few lines, head, bulldozers, and even tab completion works here. Jupyter does everything. Right, so here's the first 5 lines, okay? So there's like a bunch of column headers and then there's a bunch of data. So that's pretty hard to look at. So what we want to do is take this and read it into a nice tabular format, okay? So does Terence put his glasses on mean I should make this bigger, or is it okay? Is this big enough font size for everybody? Okay. So this kind of data where you've got columns representing a wide range of different types of things, such as an identifier, a value, a currency, a date, a size. I refer to this as structured data. Now, I say I refer to this as structured data because, like, there have been many arguments in the machine learning community on Twitter about what is structured data. Weirdly enough, this is like the most important type of distinction is between data that looks like this and data like images where every column is of the same type. Like, that's the most important distinction in machine learning, yet we don't have standard accepted terms. So I'm going to use the terms structured and unstructured. But note that other people you talk to, particularly in NLP, people use structured to mean something totally different, right? So when I refer to structured data, I mean columns of data that can have varying different types of data in them. By far, the most important tool in Python for working with structured data is pandas. Pandas is so important that it's one of the few libraries that everybody uses the same abbreviation for it, which is PD. So you'll find that one of the things I've got here is from FastAI imports import star, right? The FastAI imports module has nothing but imports of a bunch of hopefully useful tools. So all of the code for FastAI is inside the FastAI directory inside the FastAI repo. And so you can have a look at imports. And you'll see it's just literally a list of imports. And you'll find there pandas as PD. And so everybody does this, right? So you'll see lots of people using pd dot something. They're always talking about pandas. So pandas lets us read a CSV file. And so when we read the CSV file, we just tell it the path to the CSV file, a list of any columns that contain dates, and I always add this low memory equals false that's going to actually make it read more of the file to decide what the types are. This here is something called a Python 3.6 format string. It's one of the coolest parts of Python 3.6. You've probably used lots of different ways in the past in Python of interpolating variables into your strings. Python 3.6 has a very simple way that you'll probably always want to use from now on. And it's you create a normal string, you type in F at the start, and then if I define a variable, then I can say hello, curly's Python function. Okay, This is kind of confusing. These are not the same curlies that we saw earlier on in that ls command, right? That ls command is specific to Jupyter, and it interpolates Python code into shell code. These curlies are Python 3.6 format string curlies. They require an f at the start, so if I get rid of the f, it doesn't interpolate. Okay, so the f tells it to interpolate. And the cool thing is, inside that curlies, you can write any Python code you like, just about. So for example, name.upper. Hello, Jeremy. Okay, so I use this all the time. And it doesn't matter, because it's a format string, it doesn't matter if the thing was, I always forget my age, I think I'm 43. It doesn't matter if it's an integer, right? Normally if you like do string concatenation with integers, Python complains. No such problem here. Okay, so this is going to read path/train.csv into a thing called a data frame. Pandas data frames and R's data frames are kind of pretty similar. So if you've used R before, then you'll find that this is reasonably comfortable. So this file is 9.3 meg, and its size is 112 meg, and it has 400,000 rows in it. Okay, so it takes a moment to import it. But when it's done, we can type the name of the data frame, dfraw, and then use various methods on it. So for example, dfraw.tail will show us the last few rows of the data frame. By default, it's going to show the columns along the top and the rows down the side, but in this case there's a lot of columns, so I've just said .transpose to show it the other way around. I've created one extra function here, display all. Normally if you just type dfraw, if it's too big to show conveniently, it truncates it and puts like little ellipses in the middle. So the details don't matter, but this is just changing a couple of settings to say, even if it's got 1,000 rows and 1,000 columns, please still show the whole thing. Okay, so this is finished. I can actually show you that. So if I just type, this is really cool. In Jupyter Notebook, you can type a variable of almost any kind, a video, HTML, an image, whatever, and it'll generally figure out a way of displaying it for you. Okay, so in this case, it's a pandas data frame. It figures it out a way of displaying it for me. And so you can see here that by default, it's actually doesn't show me the whole thing. So, so here's the data set. We've got a few different rows. This is the last bit, the tail of it, right? Last few rows. This is the thing we want to predict, price, okay? And then all of the other, so we call this the dependent variable. The dependent variable is the price. And then we've got a whole bunch of things we could predict it with. And when I start with a data set, I tend, yes, Terence, can I give you this? Green box.
Hello, Jeremy.
Hi, Terence.
I've read in books that you should never look at the data because of the risk of overfit. Why do you start by looking at the data?
Yeah, so I was actually going to mention, I actually kind of don't. Like, I want to find out at least enough to know that I've like managed to import it okay, but I tend not to really study it at all at this point because I don't want to make too many assumptions about it. I would actually say most books say the opposite. Most books do a whole lot of EDA, exploratory data analysis, first.
Academic books.
Yeah, academic books.
Well, I mean, the academic books I've read say that's one of the biggest risks of overfitting. But the practical books say, let's do some EDA first.
Yeah, so the truth is kind of somewhere in between. And I generally try to do machine learning driven EDA, and that's what we're going to learn today. Okay. So the thing I do care about, though, is what's the purpose of the project? And for Kaggle projects, the purpose is very easy. We can just look and find out. There's always an evaluation section. How is it evaluated? And this is evaluated on root, mean, squared, log, error. So this means they're going to look at the difference between the log of our prediction of price and the log of the actual price, and then they're going to square it and add them up. Okay, so because they're going to be focusing on the difference of the logs, that means that we should focus on the logs as well. And this is pretty common, like for a price, generally you care not so much about did I miss by $10, but did I miss by 10%, right? So if it was $1 million thing and you're $100,000 off, or if it's a $10,000 thing and you're $1,000 off, often we would consider those equivalent scale issues. And so for this auction problem, the organizers are telling us they care about ratios more than differences, and so the log is the thing we care about. So the first thing I do is to take the log. Okay. Now NP is NumPy. I'm assuming that you have some familiarity with NumPy. If you don't, we've got a video called Deep Learning Workshop, which actually isn't just for deep learning, it's basically for this as well. And one of the parts there, which we've got a time-coded link to, is a quick introduction to NumPy. Okay, but basically NumPy lets us treat arrays, matrices, vectors, high-dimensional tensors as if they're Python variables, and we can do stuff like log to them, and it'll apply it to everything. NumPy and pandas work together very nicely. So in this case, dfraw.salePrice is pulling a column out of a pandas data frame, which gives us a pandas series, right? It shows us the sale prices and their indexes, right? And a series can be passed to a NumPy function, okay, which is pretty handy. And so you can see here, this is how I can replace a column with a new column. Pretty easy. So, okay, now that we've replaced sale price with its log, we can go ahead and try to create a random forest. What's a random forest? We'll find out in detail, but in brief, a random forest is a kind of universal machine learning technique. It's a way of predicting something that can be of any kind. It could be a category, like is it a dog or a cat, or it could be a continuous variable like price. It can predict it with columns of pretty much any kind, pixel data, zip codes, revenues, whatever. In general, it doesn't overfit. It can, and we'll learn to check whether it is, but it doesn't generally overfit too badly, and it's very, very easy to stop it from overfitting. You don't need, and we'll talk more about this, you don't need a separate validation set in general. It can tell you how well it generalizes, even if you only have one data set. It has few, if any, statistical assumptions. It doesn't assume that your data is normally distributed. It doesn't assume that the relationships are linear. It doesn't assume that you've specified the interactions. It requires very few pieces of feature engineering for many different types of situation. You don't have to take the log of the data. You don't have to multiply interactions together. So in other words, it's a great place to start. Right? If your first random forest does very little useful, then that's a sign that there might be problems with your data. Like it's designed to work pretty much first off. Can you please throw it at or towards this gentleman? Thank you.
What about curse of dimensionality when using random forests?
Yeah, great question. So there's this concept of curse of dimensionality. In fact, there's two concepts I'll touch on, curse of dimensionality and the no free lunch theorem. These are two concepts you'll often hear a lot about. They're both largely meaningless and basically stupid. And yet, I would say maybe the majority of people in the field not only don't know that, but think the opposite. So it's well worth explaining. The curse of dimensionality is this idea that the more columns you have, it basically creates a space that's more and more empty. And there's this kind of fascinating mathematical idea, which is the more dimensions you have, the more all of the points sit on the edge of that space, right? So if you've just got a single dimension where things are like random, then they're spread out all over, right? Whereas if it's a square, then the probability that they're in the middle means that they can't have been on the edge of either dimension. So it's a little bit less likely that they're not on the edge. Each dimension you add, it becomes multiplicatively less likely that the point isn't on the edge of at least one dimension, right? And so basically in high dimensions, everything sits on the edge. And what that means in theory is that the distance between points is much less meaningful. And so if we assume that somehow that matters, then it would suggest that when you've got lots and lots of columns and you just use them without being very careful to remove the ones you don't care about, that somehow things won't work. That turns out just not to be the case. It's not the case for a number of reasons. One is that the points still do have different distances away from each other. Just because they're on the edge, they still do vary in how far away they are from each other. And so this point is more similar to this point than it is to that point. So even things we'll learn about k-nearest neighbors actually work really well, really, really well in high dimensions, despite what the theoreticians claimed. And what really happened here was that in the 90s, theory totally took over machine learning. And so particularly there was this concept of these things called support vector machines that were theoretically very well justified, extremely easy to analyze mathematically, and you could like kind of prove things about them. And we kind of lost a decade of real practical development, in my opinion, and all these theories became very popular, like the curse of dimensionality. Nowadays, and a lot of theoreticians hate this, the world of machine learning has become very empirical, which is like which techniques actually work. And it turns out that in practice, building models on lots and lots of columns works really, really well. So yeah, the other thing to quickly mention is the no free lunch theorem. There's a mathematical theorem by that name that you will often hear about that claims that there is no type of model that works well for any kind of data set. Which is true, and is obviously true if you think about it. In the mathematical sense, any random data set, by definition it's random, right? So there isn't going to be some way of looking at every possible random data set that's in some way more useful than any other approach. In the real world, we look at data which is not random. Mathematically, we'd say it sits on some lower dimensional manifold. It was created by some kind of causal structure, right? There are some relationships in there. So the truth is that we're not using random data sets. And so the truth is in the real world, there are actually techniques that work much better than other techniques for nearly all of the data sets you look at. And nowadays there are empirical researchers who spend a lot of time studying this, which is which techniques work a lot of the time. And ensembles of decision trees, of which random forests are one, is perhaps the technique which most often comes up the top. And that is despite the fact that until the library that we're showing you today, FastAI, came along, there wasn't really any standard way to pre-process them properly and to properly set their parameters. So I think it's even more strong than that. So yeah, I think this is where the difference between theory and practice is huge. So when I try to create a random forest regressor, what is that? Random forest regressor. Okay, it's part of something called sklearn. sklearn is scikit-learn. It is by far the most popular and important package for machine learning in Python. It does nearly everything. It's not the best at nearly everything, but it's perfectly good at nearly everything. So like you might find in the next part of this course with your net, you're going to look at a different kind of decision tree ensemble called gradient boosting trees, where actually there's something called XGBoost, which is better than gradient boosting trees in scikit-learn. But it's pretty good at everything. So I'm really going to focus on scikit-learn. Random forest, you can do two kinds of things with a random forest. If I hit tab, oh, I haven't imported it. So let's go back to where we import. So you can hit tab in Jupyter Notebook to get tab completion for anything that's in your environment. And you'll see that there's also a random forest classifier. So in general, there's an important distinction between things which can predict continuous variables, and that's called regression, and therefore a method for doing that would be a regressor, and things that predict categorical variables. And that is called classification, and the things that do that are called classifiers. Okay? So in our case, we're trying to predict a continuous variable, price. So therefore we are doing regression, and therefore we need a regressor. A lot of people incorrectly use the word regression to refer to linear regression, okay, which is just not at all true or appropriate. Regression means a machine learning model that's trying to predict some kind of continuous outcome. It has a continuous dependent variable. So pretty much everything in scikit-learn has the same form. You first of all create an instance of an object for the machine learning model you want. You then call fit, passing in the independent variables, the things you're going to use to predict, and the dependent variable, the thing that you want to predict. So in our case, the dependent variable is the data frame's sale price column. And so the thing we want to use to predict is everything except that. In pandas, the drop method returns a new data frame with a list of columns removed, right? Well, a list of rows or columns removed. So axis equals 1 means remove columns. So this here is the data frame containing everything except for sale price. Okay? Can I have the box, or can you throw it to Ernest directly? Yes, sure.
So if you want to remove multiple columns, you just pass in a list of strings with the column names?
Let's find out. So to find out, I could hit Shift-Tab, and that will bring up a quick inspection of the parameters. In this case, it doesn't quite tell me what I want. So if I hit Shift-Tab twice, it gives me a bit more information. Yes, and that tells me it's a single label or list-like. List-like means like anything you can index. In Python, there's lots of things. By the way, if I hit 3 times, it will give me a whole little window at the bottom. Okay, so that was Shift-Tab. Another way of doing that, of course, which we learned, would be df raw dot drop. Okay? Sorry, question mark would be the source code for it. Or a single question mark is the documentation. So I think that trick of like tab complete, shift tab parameters, question mark and double question mark for the docs and the source code. Like if you know nothing else about using Python libraries, know that, because now you know how to find out everything else. Okay? So we try to run it and it doesn't work. Okay, so why didn't it work? So anytime you get a stack trace like this, so an error, the trick is to go to the bottom, because the bottom tells you what went wrong. Above it, it tells you all of the functions that called other function could cause other functions to get there. Could not convert string to float, conventional. So there was a column name, there was a value, rather, inside my data set, conventional, the word conventional, and it didn't know how to create a model using that string. Now that's true. We have to pass numbers to most machine learning models, and certainly to random forests. So step 1 is to convert everything into numbers. So our data set contains both continuous variables, so numbers where the meaning is numeric, like price, and it contains categorical variables, which could either be numbers where the meaning is not continuous, like a zip code, or it could be a string, like large, small, and medium. Okay, so categorical and continuous variables. We want to basically get to a point where we have a data set where we can use all of these variables. So they have to all be numeric, and they have to be usable in some way. So one issue is that we've got something called sale date, which you might remember right at the top, we told it that that's a date, so it's been parsed as a date. And so you can see here it's data type, D type, very important thing. Data type is date time 64-bit. So that's not a number, right? And this is actually where we need to do our first piece of feature engineering, right? Inside a date is a lot of interesting stuff. All right, so since you've got the catch box, can you tell me what are some of the interesting bits of information inside a date?
well, you can see like a time series pattern, I guess, because the time.
That's true. I didn't express very well. What are some columns that we could pull out of this?
Oh, year, month.
Year, month.
And then the date.
The date, as in, like, tell me it needs to be a number. Year, month,
Quarter.
quarter. You want to pass it to your right and get some more or behind you? Just pass it to your right. Here you go. You got some more columns for us?
Day of the month.
Day of month. Yeah. Keep going to the right.
Day of week.
Day of week. Yeah.
Anything else? The week.
Week of year.
Yeah, week of year.
Yeah. Okay. I'll give you a few more, like that you might want to think about. Would be like, is it a holiday? Is it a weekend? Was it raining that day? Was there a sports event that day? Like, it depends a bit on what you're doing, right? So like if you're predicting soda sales in Soma, you would probably want to know, was there a San Francisco Giants ball game on that day, right? So like what's in a date is one of the most important pieces of feature engineering you can do. And no machine learning algorithm can tell you whether the Giants were playing that day and that it was important, right? So this is where you need to do feature engineering. So I do as many things automatically as I can for you, right? So here I've got something called add date part. What is that? It's something inside fastai.structured. Okay. And what is it? Well, let's read the source code. Here it is. So you'll find most of my functions are less than half a page of code. Right? So here is something it's going to, so rather than having docs, I'm going to try to add docs over time, but they're designed that you can understand them by reading the code. So we're passing in a data frame and the name of some field, okay, which in this case was sale date. And so in this case, we can't go df.field name because that would actually find a field called field name literally. So df square bracket field name is how we grab a column where that column name is stored in this variable. Okay, so we've now got the field itself, the series. Okay. And so what we're going to do is we're going to go through all of these different strings, right? And this is a piece of Python which actually looks inside an object and finds an attribute with that name. So this is going to go through, and you can Google for Python get attribute. It's a cool little advanced technique. But this is going to go through and it's going to find, for this field, it's going to find its year attribute. Now, Pandas has got this interesting idea, which is if I actually look inside, let's go field equals, this is the kind of experiment I want you to do, right? Play around, sale date. Okay, so I've now got that in a field object, and so I can go field, right? And I can go field dot tab, right? And let's see, is year in there? Oh, it's not. Okay, why not? Well, that's because year is only going to apply to Pandas series that are date time objects. So what Pandas does is it splits out different methods inside attributes that are specific to what they are. So date time objects will have a DT attribute defined, and that is where you'll find all the date time specific stuff. So what I went through was I went through all of these and picked out all of the ones that could ever be interesting for any reason, right? And this is like the opposite of the curse of dimensionality. It's like, if there is any column or any variant of that column that could ever be interesting at all, add that to your data set, add every variation of it you can think of. There's no harm in adding more columns, nearly all the time, right? So in this case, we're going to go ahead and add all of these different attributes. And so for every one, I'm going to create a new field that's going to be called the name of your field with the word date removed, so it'll be sale, and then the name of the attribute. So we're going to get a sale year, sale month, sale week, sale day, etc., etc. Okay? And then at the very end, I'm going to remove the original field, right? Because remember, we can't use sale date directly because it's not a number. Okay? Can we pass that?
So you're saying this only worked because it was a date type Did you make it a date type, or was it already saved as one in the original?
Yeah, it's already a date type, and the reason it was a date type is because when we imported it, we said parse dates equals and told pandas it's a date type. So as long as it looks date-ish and we tell it to parse it as a date, it'll turn it into a date type.
Is there a way to do that so it would just look through all the columns and say, like, if it looks like a date, make it a date? Or do you have to know which one?
I think there might be, but for some reason it wasn't ideal. Like maybe it took lots of time, or it didn't always work, or for some reason I had to list it here. I would suggest checking out the docs to pandas.readcsv, and maybe on the forum you can tell us what you find, because I can't remember offhand. Good telephoning.
So how about the time zone? Like, how can we get the time zone from the...
Let's do that one on the same forum thread that Savannah creates, because I think it's a reasonably advanced question. But generally speaking, the time zone in a properly formatted date will be included in the string, and it should format it. It should pull it out correctly and turn it into a universal time zone. So generally speaking, it should handle it for you.
So I've noticed you, for indexing a column, you interchangeably use the f dot column and the df brackets of the column. Is there any consideration between them?
The square brackets one is safer, particularly if you're assigning to a column. If it didn't already exist, you need to use the square brackets format, otherwise you'll get weird errors.
Okay.
So the square brackets format is safer. The dot version saves me like a couple of keystrokes, so I probably use it more than I should. In this particular case, because I wanted to grab something that had field name had something inside it, wasn't the name itself, I have to use square brackets. So square brackets is going to be your safe bet if in doubt.
Got it.
So after I run that, you'll notice that dfraw.columns gives me a list of all of the columns just as strings, and at the end, there they all are. Right? So it's removed sale date and it's added all those. So that's not quite enough. The other problem is that we've got a whole bunch of strings in there, right? So you can just leave that there. Do you want to pass it back? Pass it back. Thanks. Sorry. So here's like low, high, medium. Thank you. Right. So pandas actually has a concept of a category data type, but by default it doesn't turn anything into a category for you. So I've created something called train cats, which creates categorical variables for everything that's a string. Okay, and so what that's going to do is behind the scenes, it's going to create a column that's actually a number, right? It's an integer, and it's going to store a mapping from the integers to the strings. Okay. The reason it's train cats is that you use this for the training set. More advanced usage is that when we get to looking at the test and validation sets, this is a really important idea. In fact, Terence came to me the other day and he said, my model's not working. Why not? And he figured it out for himself. It turned out the reason why was because the mappings he was using from string to number in the training set were different to the mappings he was using from string to number in the test set. So therefore, in the training set, high might have been 3, but in the test set, it might have been 2.